Hi, I'm Malit, PhD candidate at Northeastern University, presenting today our work on data versus instructions, runtime code generation for convolutions. So let me start by explaining our motivation. Most GEMM, general matrix multiplication libraries like Intel MKL and libxSMM now support just-in-time code generation. The reason is because small and medium matrix multiplication can be accelerated by exploiting problem dimensions. So to give a general idea on how these libraries work, so if you consider an application, for example C or C++, then you have a JIT library wrapper which allows a developer to express assembly level instructions at a higher level. So this gives a chance for the developer to perform loop unrolling depending on the problem size. And the problem size is only available at the runtime. So then the just-in-time reads in the high-level constructs and then transforms it into machine code. And the machine code can be directly executed on the CPU. JIT-based GEM solutions are widely deployed in machine learning inference and also in scientific simulations in high-performance computing environments. So this brings us to our problem. Most of the existing code generation techniques use loop unrolling and address compression. In the x86 architecture, because of the variable length instructions, with just-in-time compilers, now you can perform address compression. So let's look at the current approach. After we do the JIT process, the code will be in the text segment in the process memory. So first, the data will be copied to the data segment at initialization. For example, if we have an instruction which moves data from memory to a register, first the request is sent and then the data is retrieved from the data segment. So instead, why not just store the data value within the instruction as an immediate without using the data segment? So in our approach, first we send the data elements to the jitter, and then the jitter produces instructions which are then stored in the text segment. So now the CPU can execute the instruction because now the value is readily available. So next, let's look at our code generation process. So we use SIMD instructions, specifically AVX512, because now we can express code generation in a very compact way. Also, similar to existing solutions, we also use a custom library backend instead of using an LLVM JIT backend, because this allows us to reduce the overhead. So next, let's look at tiling. So to maximize the performance benefits, we also have to look at how we're going to utilize the available registers. AVX512 has 32 registers, each with the capacity of holding 16 floating point numbers. So first, we load the B matrix, which is the weight matrix in terms of a convolution, to 8 separate registers. And each register has the same value replicated for 16 times. So in terms of SIMD, we refer to this as a broadcast. And then we load the A matrix, which is the input to 8 separate registers. So now we can perform a vector multiplication and then the results are aggregated to 8 separate registers dedicated for the C matrix, which is the output. So the highlighted areas show the active elements in the computation. So our library Marlin can be easily integrated with existing solutions because we have a fully automated code generation. We also give the user control over when the just-in-time compilation happens. So first, the user sends a request to invoke the just-in-time process. And in step 2, this invokes our internal code generator. And at execution time, the user simply calls our convolution API. So in this case, we're using a specific Vinograd convolution. And then in step 4, it invokes our compiled kernel. So finally, the computation happens. Although in this work we target the Intel AVX 512 architecture, it can be easily extended to other platforms because most of the ISAs provide similar SIMD constructs. And for our experimental setup, we use a single socket 12-core 3.5 GHz Intel i9 architecture with a Skylake architecture, and we also enable hyperthreading. So each core has access to two AVX512 FMA units. So we compare the performance of Intel MKL SGEM, which is the traditional BLAST library, and also Intel MKL JIT API, which is the new just-in-time compilation gem. So in this graph, we can observe the normalized execution time for traditional MKL SGEM, MKL JIT, and our solution Marlin. The top and bottom graphs correspond to 32 and 64 input channels. So we can observe a performance gain of 1.12 times over MKL and 1.05 times over MKL JIT for 32 input channels. And for 64 input channels, we can observe a gain of 1.1 over MKL and 1.04 for MKL JIT. So in terms of memory footprint, due to code generation, the total size of instructions used could increase by 2.8 times because now each value is using 11 bytes instead of 4 bytes as shown in the top figure. But we can use different optimization techniques to reduce the space used for these instructions. So for example, we can express a 0 using a vector XOR operation as shown in the bottom figure. And by doing this, we can reduce the code bloat by 1.8 times. So this is especially important when you have a convolution with a sparse weight matrix. Most of the time, we're dealing with sparsity in weight matrices. So this gives a chance to further optimize the instruction size by exploiting the inherent sparseness available in convolution weight matrices. So this brings us to our conclusion. So we developed a unique way of generating code at runtime based on data. So current approaches only consider the algorithm level optimizations, for example, like loop unrolling and address compression techniques. But our data-oriented code generation is really important because it gives a chance to squeeze out every last drop of performance from CPUs. And for artifacts and for our open source implementation, please visit our GitHub website provided here. Thank you for joining with us today.